Welcome to the Quantum to Cosmic YouTube channel with me, Ollie. Welcome back to this tutorial series on functions. This series is aimed at first year undergraduate university students or those who are just interested. Whether you just need a refresher on these topics or are learning them for the first time, you're in the right place. Today we're continuing with partial differentiation, looking at partial differentiation for converting between Cartesian and polar coordinates. So if you're ready to learn, then let's get into it. In Cartesian coordinates, u would be a function of x and y, and in plane polar coordinates, it'd be a function of r and theta. And I've used the overbar on u, i.e. u bar here in plane polar coordinates, because these functions wouldn't be the exact same description even though they're describing the same function values. So for example, just to make that clear, u being x squared plus y squared does not mean u bar will be r squared plus theta squared to get the same values as x squared plus y squared. Instead, it would actually just be r squared. That's why this bar will be used for talking about plane polar coordinates. Our conversions between Cartesian coordinates and plane polar coordinates will be x is equal to r cos theta and y is equal to r sine theta for going from plane to Cartesian. And then for the opposite way around, it will be r is equal to x squared plus y squared, all square rooted, and theta is equal to arctan of y over x. So for an example, what is partial dx by dr? And we would find that it's just cos theta. And then if we did the inverse of that on the other side, and said, what is partial dr by dx? We'd get x over x squared plus y squared, all square rooted, which is an identity and is just cos theta as well. And you might be tempted to say, okay, well therefore, if partial dx by dr is cos theta, and partial dr by dx is cos theta, then therefore partial dx by dr equals partial dr by dx. But similar to what we had previously, in these cases of partial differentials, we aren't keeping the same thing constant. For this dx by dr, we're actually keeping theta constant, whilst for dr by dx, we're keeping y constant. So here we can't say that these partial differentials are equal because we're keeping different things constant whilst working out that differential. So it's an important note to think about there. But we can easily do all the rest of the partial differentials like dy by dr, etc. And I'll leave that to you to do as an exercise. So we might want to apply the chain rule. So if we say partial du by dx, what's that equal to? Well, it's going to be partial du bar by dr, partial dr by dx, plus partial du bar by d theta, partial d theta by dx. And this will be going from, on the right here will be our polar coordinate, so we've got just du by dr, and then dr by dx is going to be using what we've got here, this dr by dx, and similarly for theta. And then we can do the same for y, so what is du by dy? Well, that's equal to du bar by dr, partial dr by dy, and you get the picture. Same for theta. And we can substitute in for our known partial differentials, so the ones not involving u bar, as that's a function to define, and we can see that this dr by dx will be cos theta as we found before, partial du bar by dr, plus minus sine theta over r times partial du bar by d theta. And then for du by dy, we'll have sine theta du bar by dr plus cos theta over r du bar by d theta. And now if we take out u and u bar from these functions, we'll see that in the first case we have partial d by dx is equal to cos theta partial d by dr minus sine theta over r partial d by d theta. And you can see all I've done there is just take out the u bar in there and take out the u for the partial du by dx. And then we can also do the same thing for partial du by dy, and we'd get partial d by dy is always equal to sine theta partial d by dr plus cos theta over r d by d theta. And these are known as our partial differential operators. And these relate rates of change in the two different coordinate systems, so we can convert from one to the other. In this case, we'll be trying to find our Cartesian coordinate rate of change on the left using our rate of changes for polar coordinates on the right. So for our first example, we might consider this function of x and y, u, which equals x squared minus y squared, and converting that into polar coordinates would be r squared times cos squared theta minus sine squared theta, and that would be our u bar. That's the difference between u and u bar. One is in terms of r and theta, and one is in terms of x and y. They aren't identical functions, but they represent the same values. If we wanted to know what is partial du by dx, we could quite simply do it in this example from our function u of x and y. And we just see this is 2x, and if we convert that into polar coordinates, that's 2r cos theta. Just to verify that our partial differential operators work successfully, let's use them and see if we get the same result. So we first might want to know what is du bar by dr, and we can find that that is going to be 2r times, and here I'm going to use a shorthand. Instead of writing cos theta or sine theta, I'm just going to write c or s respectively. So here it will be c squared minus s squared. And then for du bar by d theta, we're going to keep our r squared where it is, and this will become minus 2 cos sine minus 2 sine cos. And now if we combine those, we just have minus 4r squared times cos and sine. So now we can put these into our functions. This d by dr and this d by d theta is what we've just worked out, where we've got our u and u bar in the right places. And so our partial du by dx is equal to cos theta times du bar by dr, so times our 2r cos squared minus sine squared, minus sine over r times our minus 4r squared times cos and sine, and the minuses will cancel, so we're left with sine theta over r times 4r squared cos and sine. And if we multiply these out, we'll be left with 2r times cos theta times our cos squared theta minus sine squared theta, added to 4r times sine squared theta times cos theta. And here I've written out the cos theta to separate for this next bit. It will make it more apparent what I'm trying to do. So if we take on one side our factors of cos squared theta and on the other side our sine squared theta, you'll see what happens. We have 2r cos theta times cos squared theta, and then for the sine squared terms, we'll have plus 4r cos theta sine squared theta minus our 2r cos theta sine squared theta from this term here. And so combining these last two terms, we're just left with 2r cos theta sine squared theta. So we can get rid of that and just make that a 2. And now you can see this is just 2r cos theta times cos squared theta plus sine squared theta, which equals 2r cos theta, which is our 2x. So we can be confident that our partial differential operator is working as expected. And I'll leave it as an exercise for you to find out what partial du by dy is. Well, you'll know that it's just minus 2y, but I want you to go through the partial differential operator method to find that it is minus 2y. So now we'll move on to some more general equation finding rather than using actual examples for u. So what if we wanted to find partial du by dx squared plus partial du by dy squared? Well, for our du by dx squared, we can just substitute in our expression for the partial differential operator, and we'll have cos theta times partial du bar by dr plus minus sine theta over r times partial du bar by d theta. And that's all squared. And we can do the same thing for y. And if you combine all this, and I'll let you do it as an exercise, we get that partial du by dx squared plus partial du by dy squared in polar coordinates is partial du bar by dr squared plus 1 over r squared times partial du bar by d theta squared. So quite a satisfying result. The only difference really is that 1 over r squared. For our final example, let's look at Laplace's equation. And if we wanted to convert this from Cartesian to polar coordinates, where partial d2u by dx squared plus partial d2u by dy squared equals 0, and we want to know what's the equivalent expression for u bar, r and theta, well, let's start with this first term, partial d2u by dx squared. So we can split this into the two operations that are happening. First we have partial du by dx, and then we apply partial d by dx on top of that. And then if we substitute in our partial differential operator here, times the same expression where u bar is applied on the differentials. And after multiplying these out, where all these differential operators will apply on both terms, like this, and after a lot of calculation, we'll end up with these terms. So pause now to check that you end up with the same terms. And what we can then say is the same thing for d2u by dy squared. And again, we'll just substitute in our partial differential operator for y, and you should end up with the following terms. And again, pause now to check that you've got these results, because now we're going to combine them to use in Laplace's equation and find our polar equivalent. So if we just add them all together, you will end up with, and again this will take some more algebra, but you will end up with that partial d2u bar by dr squared plus 1 over r times partial du bar by dr plus 1 over r squared times partial d2u bar by d theta squared. And these first two terms are usually combined into one term, which is the same as 1 over r times partial d by dr times r partial du bar by dr. And if you times that out, you'll see you do get the same thing. And then we can plus our 1 over r squared d2u bar by d theta squared. And that is equal to 0. That's our Laplace's equation in polar coordinates. And this will be used throughout physics, especially when you get into 3 dimensions, and the Cartesian version of that is just adding on another d2u by dz squared, but for spherical polars we'll have another angle, phi, and for cylindrical coordinates we'll have z the same, but it'll be a much more complicated expression, and this can be used throughout physics. You'll see it come up. Today we've learnt about converting between Cartesian and polar coordinates. In the next video we'll be looking at implicit functions. So if you want to learn more, I'll see you in the next one. If you learnt something new or just enjoyed this video, please hit the like button and don't forget to subscribe and tap the notification bell to stay updated on new videos. In the meantime, stay curious and I'll see you in the next one.